So welcome back to the Europlanet webinar on planetary defense. Just watched a very nice documentary produced last year in France. It's time for the talk part of our session. And let me introduce our speakers. We have two speakers for you today. First, we will hear from Richard Moissl. He is a planetary scientist and works at ESA since 2011. His scientific focus is on small bodies of the solar system. At ESA, he first worked as a liaison and operations scientist for Bepi Colombo and Rosetta, also supported the Asteroid impact mission and later the Hera mission that we heard a lot about in the film, and we will hear more about in the talks. He now works at the ESA Planetary Defense Office since 2020, first as a mitigation activities coordinator, and since 2022 as the Planetary Defense Officer. Then we will hear from Patrick Michel, who is a director of research of exceptional class at the French Scientific Research National Center, CNRS, and works at the Lagrange Laboratory of the Observatoire de Côte d'Azur in Nice, France. He's also a global fellow of the University of Tokyo. His scientific specialty, of course, is impact processes between asteroids, which makes him the perfect person to be the principal investigator of the Hera mission at ESA. He's also co-eye on the Ramses mission, also from ESA, to the asteroid Apophis, about which we also heard in the film. Finally, his name is already in the sky as asteroid 7561, Patrick Michel. But so let's start our first presentation by Richard. So Richard, if you can please share your slides.
Okay.
Perfect. Okay.
Then good afternoon, everybody. It's a pleasure and an honor to be here and to be given the opportunity to talk about our work with you. I think that film was already a fantastic introduction. I think I don't need to spend a lot of time to introduce or to motivate what asteroids are. So just a very quick one. The historic naming comes from like a star. So they are like stars, but they move. They're also called minor bodies. As we've heard, there are lots and lots of them in the solar system, way more than a million, actually several millions. In reality, it's just more than 1.3 million are known today. They come in all sizes, shapes, and everything, and compositions, as we've heard, but the only thing that is common to all of them is that they move on Keplerian orbits, perturbed Keplerian orbits about the Sun. So what we mean by near-Earth asteroids are those who get close to the orbit of Earth. So whenever the orbit of the asteroid is equal to or closer to 0.3 astronomical units from the orbit of Earth, at the closest encounter point, we classify an asteroid as a near-Earth asteroid, or mixing together asteroids and comets as near-Earth objects in general. So they are of particular interest for our field of work. So to date, there are about 38,000 near-Earth asteroids known. Watch this space. This number will change significantly more later. And about 1,800 of them are special because the vast majority, as you can see in this little animation, this is not just an animation of colorful dots. This is really a graphical representation of what is in our ESA internal database of all the known near-Earth asteroids. The vast majority of them is entirely harmless for us. About 1,800, this is a graphical representation of the subset, have the ability to cross the orbit of the Earth when Earth is there within the next 100 years, which means that there is a non-zero risk of impact of the asteroids. The position is not known perfectly well, and the more you interpolate positions into the future, the more uncertain it becomes. So these uncertainties it's probabilities, as was mentioned also in the movie. But these are essentially the ones that are of most interest to us. That's the daily work to follow them up. So I've referenced the daily work. So, but first of all, I think we've got a good impression from the movie, but I think I'd want to stress the fact that often people equate asteroid impact with the end of the dinosaurs, or with the end of the world as we know it. But there's plenty of minor bodies in the solar system. So they come from all kinds of sizes, from micro-sized particles that just produce the zodiacal light, and up to 30 to 100 tons of this material is raining down on Earth every day without any consequence. Once we get to centimeter-sized particles, we get nice shooting stars. They are pretty, they're still harmless. When we reach the meter-sized particles, things get more spectacular. We get so-called bolides that have visible representation in the atmosphere, and often drop meteorites. This one is, for example, a film from, or a little clip from Berlin in early 2023, where the asteroid 2023 DX1 hit, and meteorites were subsequently found. As we've also seen in the film, once we get to 10 meter size and larger, then things become interesting, and then they become relevant for planetary defense purposes. This one is another representation of the Chelyabinsk impactor in 2013. And here we spectacularly see that it outshines the sun. We've heard an estimate in the film, I think about 20 Hiroshima bombs, as total estimates go from 20 to 30 something Hiroshima bombs. So this is where it's already important to know that asteroids are coming, and to be able to see them ahead of time, and to accurately predict whether they will impact and where. When we go to about 50 meters in size, we see even more spectacular features, like was also referenced the Tunguska event in 1908, which flattened 20,000 square kilometers of forest, 2,000 square kilometers of forest, sorry, or the Arizona impact crater, also called Barringer crater, which was caused by a 50-meter solid iron impactor. And here you see the nice difference, or the interesting difference. Solid iron made a big crater, while a more fluffy, presumably rubble pile object flattened with a shock wave. They're both equally dangerous to urban centers, and this is why 50 meters is an important waypoint in international planetary defense. I'll touch on that later. This goes on and on and on. We've heard about the 150-meter mark, where asteroids become stitched with the label potentially hazardous, and more than regional damage is to be expected. And it goes all the way up to global catastrophes, as we know from the stories, to the, let's say, the Hollywood regime. Together with a big international community, ESA is recognizing the asteroid impact threat as one of the three major threats from space. Among space weather, which is a repeatedly recurring threat. Right now, we are in the maximum of the solar cycle, so there is a lot of space weather recently. You might have seen it in the news. And the constant and growing problem with space debris and non-maneuverable space assets in the face of ever more space traffic evolving. This is also a major threat. And then last but not least, our, let's say, very probability-based work comes in here. So who are we? I've referenced our daily work. We are indeed a small set of professionals which integrate all of the basic aspects of planetary defense in one place. This is very rare on Earth. There's to date only two fully end-to-end segments, one in NASA, one in ESA. The Japanese colleagues are right now also establishing their planetary defense unit. And I've heard that also CNSA in China has started hiring a team of professionals to do it end to end. So our mandate is to protect the planet, of course, from dangers in space. And we're tasked with detection of near Earth objects, assessing their impact probability, and supporting mitigation activities. These people really exist. This is our logo. Little side joke to don't look up. So who are we physically? We are a team of professionals of about 16, 17 professionals by now, spread across several sites in Europe. Our headquarters is the so-called Near Earth Object Coordination Center at the ESA site in Frascati, near Rome in Italy. And you see a little glimpse into our daily way to work and into our facility. But we also have people stationed at ESOC in Germany, where I am at the moment, at ESTEC in the Netherlands, and at ESAC in Spain. It's mostly observers that are spread across Europe, but also technical experts. And our workflow in a nutshell perfectly represents our tasks. So first of all, you can only react to what you know and what you've seen coming. So the first pillar of our observations, of our work, is observations, of course. Then the second, and I would say the core pillar, is the assessment of impact probabilities, and hand in hand with that, the provision of the information, because our mandate covers immediate or as near real time as possible and direct communication of all the information available that is relevant. And last but not least, of course, supporting and developing mitigation activities. Observations, I'll start with the first pillar. Theirs can be split into two, let's say, regimes. The first one is the survey duty. You need first to find them, that's discovery. And then, as was also hinted in the movie, follow-up. As you've learned in the movie already, this is a global work. So, for example, the big survey networks, the Pan-STARRS or the Catalina Sky Survey, they are being operated by our colleagues at NASA, and we are now finally also doing a contribution to the big survey networks with the FlyEye telescope networks. The first one is being commissioned in Matera in Italy right now. Here's a little explainer I have how you can visualize what is happening. So usually the same area of the sky is revisited a couple of times a night, and then you can see that the stars remain stationary, but asteroids move in front of that. And these moving objects then get evaluated for parallax and everything, and then you can extrapolate first guesses at their trajectories. Here is a little close-up on our FlyEye. On one side, you see the artist concept, and the thing that makes it very novel and gave it the name FlyEye, it's a 1 meter mirror, but instead of having a secondary mirror, it has this 16-faceted prisma that splits the beam onto, and here we see a real image of the telescope right at the moment in its mighty mount at Matera, with 16 high-performance, high-resolution cameras that allow it to have a humongous field of view of 6.7 by 6.7 degrees and still sufficient resolution to do precise astrometric measurements. We are right now commissioning it in Matera, but it will finally take up its duty mid of next year at the top of Monte Mufara in Sicily. But already now it's surprising us with its very nice performance in images. Second step in observations is the follow-up. This is something ESA is traditionally focusing on. So in the recent 1.5 decades, this was the main focus of our observatory work, which is now expanding, so to speak, to the survey network. So we own several assets ourselves, the so-called testbed telescopes at Cerbero, Spain, and on the other side of the planet and the other hemisphere at La Silla in Chile, but also, for example, the 1 meter optical ground station at Tenerife. We also have partners across the world. We collaborate with the CLED telescope in Czech, the Himalayan Chandrayaan telescope in India, and up to the very large telescope in Chile, and many, many more. There's an entire network, and it's a mix of our own assets, of telescopes where we have time available, or where we have service level agreements for companies that perform the observational work and collaborate with us. This all, of course, is embedded in the greater collaboration of worldwide planetary defenders. It cannot be stated enough. This is a global job. This is not a one man, not a one agency job, not a one country job. This is all of us together. But as many telescopes as you put up, they can only observe on the night sky. Things like Chelyabinsk would still come through undetected. And this is why NASA, for one, is launching the NEOCC telescope. I think it was referenced in the movie. Sorry. It was referenced in the movie, but we are also establishing the first ever first ever early warning system for asteroids on the sunward side of Earth, to be operational in the 2030s. The name of the study is NEOMIR, Near Earth Object Mission in the Infrared. We might come up with a more descriptive name in the future for that one. So the second and core pillar of our work, again, is the assessment pillar. So that's typically 3 steps. Orbit determination of the orbit that is determined via the measurements. Sorry, one moment. And then last but not least, the warning of imminent and not so imminent impactors. So the warning systems, they are split into 2. The first one is the quick warning or early warning of imminent impactors. That's the so-called meerkat system, named after the little animals, where always one of them is standing guard to take care of threatening situations to the rest of the herd. While our main system, this is a real big computer, is determining the orbits for a total of 100 years into the future, calculating and monitoring the impact probabilities. And this is not just the immediate trajectories that are being calculated, but it includes all perturbations and all kinds of stochastic fluctuations on the orbit that cannot be predicted, that are just, within the measurement errors and everything. So this is a humongous amount of calculations. It's about 100,000 orbits for every of the objects for 100 years, really propagated in a trajectory propagation. That's a lot of work. But the result is worth all the work. We arrive then at an estimate whether an asteroid might have an impact with Earth. That is, whenever the uncertainty region in the future is overlapping or engulfing, in some cases, Earth at some point in time. Any asteroid that fulfills this criteria gets listed on our risk list, where they're ranked after their, let's say, impact probability and their technical dangerousness, marked on the Palermo scale, which is a technical scale. I'll be happy to provide answers for in questions and answers. But we also provide lots of information, for example, on close approaches, with some indication on whether there are frequent events, infrequent events, and everything. So I can heavily recommend to search just for risk list ESA, and you will come to our portal and see all this listed there. Exactly. So, and there are many, many more information provision tools that we have available. For example, we have an orbit visualization tool where you can visualize individual or whole populations of asteroids, flyby visualizations. I can, of course, recommend the flyby of asteroid Apophis in 2029, which is very highly detailed there, and many other tools which are very useful and or entertaining. Please give it a stop by on our webpage. This is all extremely useful. The third and last pillar is the mitigation. So in short, it's the answer to what happens if we have an asteroid that has unusually high impact probability. So the first thing, again, is international collaboration. Our Aegis system is basically completely mirrored on the NASA side with the Sentry system. And whenever there is anything out of the usual, we do a quick consistency check between the systems. Actually, there's a third one, NEODICE in Italy. And when they qualitatively agree, then we can raise notifications and alerts. And even in the case of 2024 YR4 recently, we have even informed national entities of the risk scenario directly. This all is embedded, again, in international collaboration. There are 2 UN-endorsed working groups, which really cannot be understated in their importance, and which have been exercising this activation for the very first time ever. There is the International Asteroid Warning Network, which is pronounced colloquially IWARN, like I warn. This is currently organized by NASA as a secretary. And this is a very, very big community. Everyone who demonstrates that they can participate in the observation or calculation or do anything that furthers the information about potentially threatening asteroids can become a member of the International Asteroid Warning Network. So naturally, it has more than 70 members by now across the world. And it's a wide mix from state actors, space agencies, up to individuals who are greatly participating. The second big group is the Space Mission Planning Advisory Group. And this group gets activated. So the activation criteria for I1 are if an asteroid with more than 20 meters in diameter and an impact probability of more than 1% within the next 50 years is discovered, this network is being activated to coordinate worldwide the information gathering and dissemination. If an object exceeds the threshold of 50 meters, you might recall from the previous slide that from 50 meters, we really have damage equaling the size of population centers. And there we don't want to be exposed to this. We don't want to take a hit like this as humanity, because it might hit one of our population centers. And even just the damage, if you were able to evacuate everyone in time, it would be prohibitively large. And this is why from 50 meters, the Space Mission Planning Advisory Group sits together. This is basically a working group composited of several space agencies across the world. And then space-based countermeasures are being proposed. Same page is involved in things like DART and Hera. It was instrumental in promoting these activities and in future missions. All of this gets then reported to the United Nations, which can then pass resolutions in case of an emergency. There are many more services. I will try to speed up a bit because I see that my time is progressing rather quickly. So we provide effects simulations upon request. And I can reference that one part of the mitigation activities is, of course, the AIDA cooperation. I don't need to reference this. Patrick will take this. I just want to say that we've been live viewing the DART impact from ground here. This is one of our observations, and it was amazing. We hadn't anticipated it to be that spectacular. Even seasoned astronomers, when seeing this, were like, "Oh, is it still there at all?" The small one. So it was quite an exciting thing also for those looking from the sidelines. There's some other impressions, but I leave that to Patrick. Hera has recently demonstrated an incredibly autonomously guided flyby at Mars. But that's where we are at the moment. Are we anywhere near the end? No, on the contrary. As I might have hopefully pointed out successfully, we are still closing severe operational gaps. We're still working on bigger surveys, observing the day side. We need to enhance and upgrade our capabilities, become faster, more accurate, include more efficient methods, get more bang for the buck. And of course, we need fast asteroid reconnaissance deflection capabilities, because once we discover the threat, time is of the essence. Patrick will also go into that a bit. We see that in recent years, the discovery rate of near-Earth asteroids has practically steadily increased. This is just a partial statistic for 25, and there was some maintenance works here, but in essence, we're getting better and better and better. And this will go potentially higher, it will exponentially go higher. Not just the Flyer, but also the Vera Rubin telescope, as was mentioned, within just a couple of nights of observations, more than 2,000 main belters, 7 new NEOs, just like that in testing. It was just a tiny sliver of the sky. This is a beast. It will make these numbers explode. Then we have NEOCC and NEOMER boosting the other side. So there will be lots and lots of work. There's also the Apophis encounter upcoming, a highlight for the entire planetary defense community. And this has led to the designation of the year 2029 as the International Year of Asteroid Awareness and Planetary Defense. I'm really looking forward to gaining a year with opportunities and highlights to demonstrate that the work we're doing is maybe not immediately relevant at the moment. I hope it is. But it might become super relevant at some point in the future. So we are working for our kids and their grandchildren and the future generations here. With that, I think I can conclude my part of the talk. Thank you very much for your attention.
Good. Okay, so thanks a lot for inviting me to give this talk. Actually, Richard introduced nicely what I'm going to say. I will go a little more in detail and focus on the ESA contribution to planetary defense in terms of space missions going to rendezvous with the asteroids and not observe from distance. And in particular, we have two missions, one already flying Hera and the other one in development, pending formal approval at the ESA Council at ministerial level in November 2025. And I will cover both of them. So as you know, Hera takes place in the framework of the AIDA collaboration. AIDA stands for Asteroid Impact and Deflection Assessment. It's a collaboration that supports the two missions, DART and Hera. So in the movie we just saw, we saw the impact of that on Dimorphos, which is a small moon of the binary asteroid Didymos. It's about 150 meters in size. It rotates with an orbital period of 11 hours and 55 minutes initially. And Didymos is about 800 meters in size. So that was launched in 2021, made the impact on September 26, 2022, US time, because in Europe it was early morning, September 27. Before impacting, it released a small CubeSat called VishaCube from Italy 2 weeks before impact, so that we could have some images of the impact itself. And then later on, the European Space Agency launches Hera, which is a sort of a detective that goes back to the impact scene and tell us about what happened and what is the final outcome. So it was already very successful. There were more than 100 papers in peer-reviewed journals from just the DART itself, predicting what Hera will see. So it's really already a great success that our American achieved. This is how it was done. So DART arrived at 6 kilometers per second in the direction opposite to the motion of Dimorphos around Didymos, so that we could basically slow down the orbital period. The question was how much we would reduce the orbital period from the initial one, and so that give us a measure of the efficiency of the deflection. In order to measure the orbital period, how we do it, if we do it close enough to the Earth, and the impact took place at 11 million kilometers from Earth, and that was really because of that we chose Didymos, is because we knew that in 2022 it would come close enough to the Earth that we could measure what I show here from the Earth, which is the reduction of light of Didymos when Dimorphos comes between the Earth and Didymos or goes behind, and the time between two reduction tells you how much time it needed to make one turn around Didymos. You do it before the impact, you measure 11 hours 55 minutes, then you make the impact, you do it afterwards, and then you see how much it was reduced, or if it was not reduced because we missed it. So the launch was effectively done on the 24th of November 2021, so that DART would arrive at Didymos when Didymos and the Earth are at their closest distance. So it was 10 months perfectly calculated, so that after 2 hours after launch, we knew exactly when it would hit on the 26th of September 2022. And you can see the trajectory of DART, Didymos arriving, and then DART would intercept actually the system when the system and the Earth are the closest. So perfectly timed. So this is the last 5 minutes where the smart nav, the navigation smart system with images provided by the Draco camera, try to lock on Dimorphos using light points as reference. And the movie is not super smooth because the thrusters have to readjust the trajectory of that, so that we always have Dimorphos at the center. And then you have the last images where we all screamed like babies, that we are actually. And this is the last image where, of course, the DART spacecraft exploded, and therefore we couldn't transfer what was the last image. We also had some images from the ground. This is Atlas telescope, where you could see the dust released by the impact. Actually, just after the impact, when we saw this image, we saw that we exploded Dimorphos, and we were wondering what Hera would see when it arrives, maybe a ring around an asteroid. We're a little scared. Fortunately, we found Dimorphos later on, so it was still alive. And by doing again the measurement I just showed, we could measure that the orbital period was reduced by 33 minutes. And when I say we, it's actually a large number of telescopes around the world that observe the impact. Even amateurs from every continent. Was absolutely spectacular to see this coordination of people not knowing even each other and feeding the DART team with their data, so that we could get this value of 33-minute reduction in a matter of a few days or maybe weeks. So it's really a success, even in terms of observational coordination around the world. These are the images given by LISHA-CUBE, so it's really a small CubeSat just taking pictures. It's quite impressive that they succeeded. Of course, it's a little saturated, and when you are in a low-gravity environment, a crater to evolve takes hours. So when you only have about a few minutes to observe after the impact, of course, you don't have the final outcome. You just see the first ejecta that are ejected. That allows you to get the velocity field of the early ejecta. It's still better than nothing. So that's why we could exploit this data combined with also the Hubble telescope data that show how the dust extends at tens of thousands of kilometers from Dimorphos after a few weeks, just because of the solar radiation pressure that pushes the ejecta of the size of a centimeter away from Didymos and stayed there for a long time. So really beautiful images. The question is, well, there are many questions actually, and this is why we need Hera. So first of all, the cool thing is that this is the first time we go back to a same system for which we have images, and we already know that the new images won't have anything to do with the previous one, because between the images we saw, and that you see here, and the one that Hera will get, an impact happened. And in particular, all these rocks that you see on the center of the image, this is where DART hit, they don't exist anymore. But in which state? So that's what we don't know. Then we also have the full Dimorphos, which is actually with a shape we didn't expect. It's more like an oblate spheroid, while we expected a prolate spheroid because of our understanding of how small moons of asteroids form. And again, here, these are images before. So what is now Dimorphos? Some simulations predict that it may be reshaped completely. So we didn't leave a small crater, or even a crater would just totally reshape Dimorphos, but we don't know. It also depends on the internal properties of Dimorphos. Actually, we don't know. Is it a solid core surrounded by gravels and rocks as we see on the surface, or does the surface reflect what's inside? That also we don't know. It is very important to interpret the DART impact and also to test our scenarios of binary formation. And then we also know that there are a lot of dust ejected and material, maybe boulders, out of Dimorphos, and they might also have redistributed on Didymos. So even this image of Didymos, the main body, may not reflect what is Didymos now, because it may have been covered by new material in a way that, of course, we don't know, and that's also very exciting. So we have this doesn't exist, and question mark about what the binary system look like, and whether Dimorphos was reshaped, or what's the size of the crater and the depth. And this is where we need the Hera mission. So Hera is now launched. We're going to go over that. This is a team that we have. The project manager at ESA is Jan Carnelli. The project team made a spectacular work to be able to develop such a complex mission in only 4 years. The industrial contract was signed in 2020, and it will launch in October 2024. This, I think, is the first time at AIDA that such a mission, and you're going to see it's not that simple, was developed so rapidly. So I really have a high recognition to Jan, his team, all the project team at ESA, and of course the industries led by OHB for the spacecraft, Tyvak International for one of the CubeSats, and GomSpace for the other CubeSat. They work like crazy to be ready, and everything works perfectly. So the mission objectives are effectively to better understand the impact itself and the efficiency, and also to give the final state of Dimorphos and the internal properties. The final state being what the numerical simulation of impact need to reproduce to be validated at the scale of an asteroid. And without that, they don't know what to reproduce. So this is the first time that ESA sent to for deep space exploration of an asteroid, not only one spacecraft, but a spacecraft with 2 CubeSats, which with an inter-satellite link, which communicate with the mother spacecraft their data to send them back to the Earth. So basically, it's the first time we have a multi-spacecraft approach to an asteroid, which is super exciting. The mother spacecraft can do its job. It releases the 2 CubeSats that can take more risk, going closer. One will measure the mineralogy of Dimorphos and Didymos, also see whether there is dust in the system. And the other one will, for the first time, carry a low-frequency radar that will probe the internal properties of an asteroid, which has never been done before, as well as a gravimeter, because it will land on Dimorphos. Again, first time we land on such a small body, as small as 150 meters, with a satellite. And we can even measure how the spacecraft will bounce with accelerometers. So there are many new things in this mission. Also, the first rendezvous with a binary asteroid. So I really, we can be highly impressed by ESA and by its ability to develop a mission like this in only 4.5 years. So this is a spacecraft when I explode it in a non-proper meaning, where you can see basically the wire. There are 7 kilometers of wires inside the spacecraft. This is a chemical propulsion module. These are the data handling, electrical power, sorry. Here you will see the wires, as I said, 7 kilometers of wires. This is a data handling system. We're going to go and see quickly the instruments. First of all, you have the structures that come back after the harness, the 7-kilometer cable. I'll repeat 3 times. Then the structure, the primary structure, yes, then the secondary structure that comes, and then finally the tertiary structure, which will then carry all the instruments. So you have the communication system, the high-gain antenna that is coming here. You have also the reaction wheels, which are very important, the star tracker, the inter-satellite link, which will connect the 2 CubeSats in communication with the mother spacecraft, the solar arrays. And then we go to see the sockets of the 2 CubeSats. You know, these CubeSats are only 12 kilograms, like shoebox. They have to go into this socket first. Then we have the asteroid framing cameras in the visual. We have the thermal infrared imager provided by JAXA. We have the laser altimeter. Then we have a hyperspectral imager, hyperscoot, which will give us data in mineralogy. A spacecraft monitoring camera that will observe the deployment of the 2 CubeSats in space, and then a radio science that will also allow us to measure the mass of Dimorphos. So this is all the complete spacecraft. So here you can see some tests that have been done at ESTEC with the solar panel flexibility, vibration mode to see whether it can handle the vibration of the same vibration as when it is in the launcher, etc., etc. October 7, we launched. Unfortunately, there was the Helen hurricane coming 1 week before. We knew the Milton hurricane was coming, and actually on the Monday, 7 of October, this is a picture of the Monday when we go to Cape Canaveral. It was a mess. We were 80% with 80% chance that we wouldn't launch that day, which would have been a disaster. We had another window the next day, but the weather was turning really bad, and we only had 16 seconds of window to launch. So if the guy pushing the button is coughing for 16 seconds, it's over. But a miracle happened, because 20 minutes before launch, everything calmed down, wind, rain, etc. And then we had this super launch that I let you observe was a high emotion for us.
2, 1, ignition, engines
Cape Canaveral with the
and lift off. Go Hera, go Falcon,
the
go
clouds.
SpaceX.
You can hear some people screaming and hear the clouds.
Vehicle is pitching downrange.
So of course, if you just
Stage 1 propulsion is nominal.
Bye bye Hera. This is the last image. The last image that we have our spacecraft deploying.
Hera, separation confirmed.
And now we don't have any images anymore. This is the last one. Very emotional. Contact was taken to the ground very successfully. And then it started to go into deep space with deep space maneuvers occurring as early as November. Very successful. A few burns that were necessary to put Hera on its trajectory, leading it to Mars because on the 12th of March this year, we used Mars in order to give energy to the spacecraft. So it was a swing by, but the engineers of ESA at ESOC were kind enough to offer us an additional delta V so that we could not only observe Mars to calibrate our instruments, but also one of the two moons, as Richard showed, Deimos, which is the most distant one, which was very amazing. As you will see, this is a geometry of the swing by. So Hera is arriving like this. It will pass by Deimos at 1,000 kilometers, actually even at 300 kilometers, but the last image is taken at 1,000 kilometers, then approach Mars again, and then go away to reach Didymos. So that was really great because we could hope to do some science along the way. It was just an operational flyby, but ESOC people are fantastic and they really achieved a great trajectory maneuver to make us see Deimos in the field of view. And this is a movie showing you the real images. And 9 days before approach, you start to see Mars coming in the field of view. And then we will also use natural feature tracking. We will test the natural feature tracking system, which is a sort of an autonomous navigation system. So we take some references on Mars, and then the spacecraft is guided by these references. This is what we will use at Didymos to do autonomous navigation, and it was successfully tested at Didymos, and GMV in Spain is highly involved in that, also a great industry working in this mission. This is an image by the Hyperscout imager of Deimos. Mars is blue because it is taken in the blue range of the hyperspectral imager. You can see Deimos is very dark, it's 12 kilometers in size. This is an image in the thermal infrared this time. I need to point out that these are images of Deimos on the side of Deimos opposite to Mars. We have very rare image. Only the HOPE mission by the Emirates took images on this face of Deimos. So we are the second one only. All other images come from orbiters of Mars, and they usually see the face of Deimos facing Mars. So we have a new science here because we have wavelengths that other missions like HOPE don't have to observe Deimos. We are still calibrating the data. We don't have yet all the calibration done, but already we see very cool things, so we are preparing papers. So although it was just an operational maneuver, we could do some science, and it's very exciting. You can see now what's coming on. And in fact, just to say that we start the early characterization phase in November 2026, which is 1 month earlier than planned. It was December, but the operation team again succeeded to save us 1 more month. And for scientists, every second counts. So I'm very happy to start the operation at close proximity November 2026. We have a community website where you can find a lot of information. There is even an Hera AI. I recommend that you connect and make a login, because then you will be able to talk with Hera. Also, you have the telemetry, you have many information, you can ask any questions. Soon you can even have the voice. It's absolutely fantastic, even for educational purposes. So I recommend that. So finally, I would say, and I will just talk 2 minutes about Ramses. Martin, you tell me if I'm way over my time. But as you can see, we have a lot of images of asteroids now that reveal their incredible diversity in terms of size, shapes, physical properties. And even on one asteroid, you have an incredible diversity of geological features, from landslides to craters to boulder fields to lineaments to even ejection of particles. It's absolutely incredible. This is because we go there to observe them, but not only. What we found is that when you touch an asteroid, sometimes the behavior is not the one you expect from the images, because they behave in a very low gravity environment, and therefore their behavior can be very counterintuitive. This is why we either need to touch to provoke an interaction, or luckily, with Apophis coming in on April 13, 2029, we don't even need to touch. There will be a natural interaction occurring, because on this day, the tidal forces of the Earth will have an influence on the physical property of Apophis. So here you don't even have to touch to make an impact, to take a sample. You just observe what happens. And this is so unique because it's only every few millennia that such a big asteroid comes so close to the Earth, 32,000 kilometers from Earth, that UN, United Nations, declared 2029, the International Year of Asteroid Awareness and Planetary Defense. So we'll organize many events around the world during the whole year. And this is why also ESA is now developing, again, pending formal approval in November by the member states of ESA, the Ramses mission to launch in May 2028, arrive at Apophis in February 2029, and then observe how the physical properties can be modified by the tidal forces of the Earth. Again, this is a small scale of Hera. We don't have time to develop the mission. It's only in 3 years that we need to launch. So we use what's existing. Hera was so successful to be developed in only 4 years that using the same platform and adapted to Apophis is the best thing to do. And that's what is now done. Of course, the objective I just tell them, but this is how we adapt the platform of Hera to Ramses. Apophis come closer to the Earth, we can shrink the solar panels and also the antenna. However, you have a higher delta V, so you need a larger tank. But basically, this is transferred from one platform to the other. We have also international cooperation with JAXA, with the thermal infrared camera, like on Hera, the same, lightweight solar array, and maybe even the launcher. This is still under discussion, under study, but we could also have a contribution of the launcher. So JAXA is heavily involved. And there are synergies with other missions that plan either to do a flyby of Apophis or a rendezvous, the Osiris Apex, which now is under threat. But I really hope it will come because it would arrive a few weeks after Ramses and we could do complementary science. It would be really exciting and also a good demonstration of international cooperation. I won't go into the detail because I think I passed my time. But just to say that, again, the launch will be in May 2028. We have a lot of instruments, a great team, and the 2 CubeSats under study, including a seismometer if one of the CubeSats land. And this will be the first time that we do seismology on an asteroid, measuring how the seismic waves propagate when the asteroid is experiencing tidal forces from the Earth. So I stop there, and I thank you very much.
Thank you so much, Patrick. Thank you so much, Richard, for your amazing and very, very interesting talks. Looks like we will have to invite you back soon because there is so much happening next year and the coming years. So thank you very much. There's time for questions. So if anybody from the attendees has any questions, please type them in the chat or in the Q&A box. Or if you want to speak, I can unmute you. In the meantime, people write their questions. So when is FlyEye going to be operational? What's the plan?
The plan is for the first unit to become operational around mid next year.
Okay.
So right now we are assembling the first telescope of this type ever built on the planet, and only in in April, May, the parts have for the first time ever been put together. It has been separately developed as the mount and the optics. So we are now, of course, commissioning the whole thing. It's a bit like a space mission in terms of complexity and size and everything. But we're making good progress. And meanwhile, the final observatory is being built in Sicily. But that all should be concluded by next year. And then we hopefully can immediately start with the second, even redesigned, even better, newer and better version in South America.
Okay, so you were saying before we started the webinar that already you did some commissioning, so there's already some baseline tests that you did, and you saw already, like, I don't know how many asteroids, correct?
Not a lot of asteroids, but
okay.
We checked how deep we can go, and it was a bit deeper than expected.
Right.
So we are at 20.5 magnitudes in a site that is not meant for dark sky for astrometric observations.
Right. Okay, excellent. Then of course we planned this webinar also in this time frame of the year because it's Asteroid Day coming up. It's in next week, right? Would you like to comment on that, Patrick, Richard? I don't know how much you are involved with it.
Yeah, I can just say that, effectively, thank you for saying that because it's the 10th anniversary of Asteroid Day. So it's not only Asteroid Day. So just to remember, Asteroid Day was initiated by Brian May, the guitarist of Queen, the legendary guitarist of Queen, and also astrophysicist, with a few colleagues, and Greg Richter, also a movie maker, and others. And then just to remember the explosion of a bolide on the 30th of June, 1908, over the Tunguska forest in Siberia that pulverized 2,000 kilometers square of forest. And in order to raise awareness, not to generate fears, on the contrary, is to say, look, of course, you have movies showing you catastrophes, etc. But wait, there are people working on it to be able to eventually get a plan. So it's in order to, in fact, explain what people are doing, emphasizing that we don't have any identified threats. So we don't do that because we need it. We do it before we need it, so that we don't have to improvise. And all these concepts are part of this Asteroid Day. So every year there are events actually everywhere in the world. One key center is Luxembourg, because there is a foundation called Asteroid Foundation that organizes this Asteroid Day, do some live streaming, etc. And it's a really educational event. So yeah, thank you for pointing it out. And you will have some live streaming in Luxembourg on the Saturday 28th. We're actually doing some panels also with Jan Carnelli, with the manager of Hera, and a few other colleagues and astronauts. So it's a great moment.
Okay, so it will be in the weekend, of course, which makes sense.
Yes.
Yeah. And Richard, is ESA going to be involved with Asteroid Day at all, or the
in Luxembourg, for example?
Yeah, of course, with the Hera mission, but
not me personal, but ESA in general. The ground-based activities. Of course, we have several small events and public talks coming up, and also some pre-made interviews. So there will be some media coverage on the day.
Excellent. Okay, there's some questions coming in. Valerio Caruba asks, do you know the minimum solar elongation of an asteroid that could be observed by the NEOMER mission? How does that compare with the NEO Surveyor mission, which should be able to reach 45 degrees?
That's what I meant with we close the gap even more. We attempt to go down as low as 30 degrees solar elongation with NEOMER. And of course, another key difference is that NEO Surveyor will do long, deep stares to catch everything in a solar system down to a size of 150 meters, regardless of whether it's on our side of the sun or on the other side of the sun. Whereas NEOMER will have a much faster pattern for the survey with more revisits. In hopes or with the intention to catch closer objects with a higher angular velocity. We've run simulations. For example, the Chelyabinsk impactor would have been detected 6 days prior to impact. So there would have been a prior warning for the Chelyabinsk impactor. And the recent case of 2024 YR4 would have been the poster case. It would have been detected a month earlier than it had been in real life. And by the time it was discovered in real life on 27th plus 2 days of recoveries, 25th December 2024, by that time, this would have constituted follow-up observations with a massive parallax to the L1 point where the observatory would observe. So we would have nailed immediately the zero impact right there.
Right. Without the need to
scare it will be a powerful tool for this,
Yeah, excellent. I hope that answered the question, Valerio. Another question by Jatin Rawal. The question is about the OSIRIS mission to Bennu. What results have been found on Bennu, or maybe will be found in the future after the analysis? We have analyzed the organics from Ryugu. Can we expect the same from Bennu, or something more?
Yeah, actually, Bennu and Ryugu are same isotopic composition. And from Bennu, there were recent analyses and papers that are spectacular. They found carbonates, which are mineral salts, which basically are the witness that there was water, salted water, brines on the parent body of Bennu. So parent body was full of water. And, this water made even veins, which are very long, actually, on the Bennu itself. We find them also on the samples, and because the water evaporates, then you remain what remain the salt minerals. So it's really the proof that we had to deal with something very rich in water at the origin of Bennu, and linked to how the water came on Earth. There is a nice story with that. And in terms of organics also, yes, of course, amino acids, even nucleobases from NRA and DNA were found. Also on Ryugu, also on Bennu. Of course, on Bennu, there are 120 grams of samples. They have also big chunks. Ayabusa 2 was a success because 5.5 grams instead of 100 milligrams is 54 times more sample that targeted. So it's really a success, but you need more time to analyze. It's very small. And on Bennu, we have 120 grams, which is twice the goal. So again, the two missions are really a success and very complementary. It's very interesting that using two missions, separate mission, picking two C-types asteroids, we find the same isotopic composition, which is connected to what we call the CI chondrites, which are the most primitive meteorites. So it's going on, but effectively, all the things that we looked for, which is what could be the relation between asteroids and the emergence of life, at least for now, are consistent with what we expected, and even more, because personally, I didn't think that we would have so many evidence of water activity from little samples from asteroids. So I think that's really exciting.
Yes, indeed. There are many more results to come, I also think. Valerio says thank you and is impressed by the 30 degrees angle. Okay.
Don't worry, Valerio. ESA is impressive. They do a lot of great things. So if Richard said we can do it, they can do it.
I agree. Any other questions here among the attendees? See, not at the moment. So of course, there's also we hear about asteroids as a threat, but there's also asteroids as a resource. And there's a lot of talk about that. We had a webinar recently about asteroid resources. So to what extent, I mean, there's an area where it becomes sort of the border lines aren't, they are quite of crossing over.
Absolutely. What I say, sorry, Richard, maybe you want to compliment, but I would say the cool thing with asteroids is that whichever objective you have to study them, what you get as knowledge feeds all objectives. Because what you need, whether it is for science, planetary defense, or resource utilization, is to better understand their composition, their structure, and how they react to internal action. Whether you want to deflect by an impact or whether you want to extract material, it's always an interaction. And therefore, when you do a mission like Hera, and you are going to characterize an asteroid, you're going to touch it with a CubeSat, you're going to probe the internal property, you're going to better understand the mineralogy at small scale, you need the same for the resources. You need to learn, because we are still at the learning stage. They are so diverse and so unpredictable. We are still as long as we are in a state where, and there is no exception so far, each time we have a new image of an asteroid, we are surprised, then it means we are still in the learning stage. Mm-hmm. And we are still there. So whatever you learn is important for both science, planetary defense, which is why it's very difficult to put in a box a space mission to an asteroid. Mm-hmm. Because, you could say it's a planetary defense mission, but also it's of science. So is it a science mission or a planetary defense mission? So the way to distinguish is how you define your requirements. And like for Hera, the requirements were driven by planetary defense objective. But of course, you have a lot of science bonus. And I would say the same. OSIRIS-REx is a science mission, but you have a return for planetary defense. And by the way, I think they were the first to really admit it openly, because in the acronym of OSIRIS-REx, you have security and resource.
Mm-hmm. Right. Yeah.
Yeah.
I don't know,
Richard, I think there's actually the fun thing is between planetary defense and in situ resource utilization of asteroid material, the list of questions is essentially the same except for the very last one where we ask will it hit us or not?
Exactly.
And resource utilization would ask the question, is there something we want to bring here? So that's the only difference.
Yeah, exactly. Yeah. So when do you think, in your opinion, will be the first time we actually going to harvest something from an asteroid? Or
I think we are still, as actually Jean-Jacques Dordain, the former DG of ESA, a former, was advising Luxembourg, was the first European state that launched itself in resources and even passed a law to allow them to exploit asteroids. He was saying, and he was very aware of the complexity, etc., is again, we need to get prepared before we need it.
Yeah.
So, which means that for now, there is no urgent need of resources in space. It would be smart if we were able, when we want to explore further, to limit the use of the resources we need on Earth, and therefore use asteroids as gas stations, so that we keep the resource we need on Earth, and then we just use what's in space. But we are not yet there, of course, because as I said, for now, each time we touch an asteroid, we didn't have the reaction we expected. So if you want to do business, you need success. And here you are still in the stage where there is a risk. There will always be a risk, but I mean, the risk is still high, too high, to start to really make sure you exploit and you have a return in terms of investment. So, but you know, for instance, the Luxembourg is fully aware of that. They anticipate on the long term. That's what they did with telecommunication, etc. And I think if all the countries have the same spirit of not, you know, dreaming that it will be tomorrow, but still being able to, but you know, it's the same for planetary defense. Huh? We don't have a risk yet. Maybe we don't have a risk for 1,000 euros. So how do you convince politicians to put money on something where you tell them, oh, you know, maybe it's not even for in 10 years, not even for in 1,000 years. It's very hard, and yet it's important because we never know, and better safe than sorry when we can do it.
Yeah,
and that applies for the two things.
Yeah, absolutely. Yeah. So, okay. I had another question, but now it evaporated. Maybe there was an asteroid coming by.
It's too hot.
Okay. Yeah. So, are there any other questions here in the audience? I don't think so. Okay, then I think we hit the hour here at 4 p.m. Central European summertime. So then we may wrap up this session for today. Thank you so much, Patrick. Thank you so much, Richard, for being here. I think it's been a wonderful discussion, and really pleased to see the film. I think it's really nicely done. Also, as a filmmaker myself, it's nice to see such beautiful productions being made. Yes. So again, as I said, we will probably invite you back next year, or when we get Hera at the system, when FlyEye becomes live, you know, and talk some more. So
Thanks a lot, Martin. Thanks for inviting us. Thanks, Richard, also.
Exactly. Thanks for being here. Nice to see you again, Patrick.
Yeah, me too. Thank you.
Okay,
Thank
bye
you so
everyone.
much.
Thank you for attending. Okay.
Bye-bye.
Bye-bye. See you next time.
Bye-bye.
Bye-bye. Bye-bye.